Okay, so last time we learned the substitution reaction with alcohol. Okay, so we've used the agent hydrogen halide or PX3. Okay, and also we learned the other one. The special case is that we use PCl5 to do substitution. Okay, and this is a good test for the presence of hydroxyl group because it can be conducted under room temperature and the expected observation should be a steaming film formed. Okay, so today's lesson, we're going to move on to the next type of reaction with alcohol, is dehydration of alcohols. So for dehydration, that means we are removing water from alcohol. Okay, so since we are removing it, we also call this type of reaction elimination. Okay, so get rid of the water from alcohol. Okay, so for this type of reagent, we can use two kinds of reactants to do, or catalysts to do. The first type, we may use concentrated sulfuric acid or phosphoric acid to do it. Okay, so by using those catalysts, we will be able to turn alcohol into alkene. Okay, so take a look at the example here. We have ethanol here. By using the catalyst and under heating, we will be able to remove the water from here. Okay, so after removing the water from the alcohol, the ethanol here, we will be able to have our product, which is the ethene molecule. Okay, so that's the first reagent, first catalyst that we can use. And the setup we use here should look like this. Okay, so we're gonna put the two solutions in here. Okay, the ethanol together with the excess concentrated sulfuric acid or phosphoric acid, and then we heat it. And then, since the ethene molecule produced here has a low boiling point because it cannot form any hydrogen bond with other ethene molecule. So once it formed, it will evaporate and then go through this delivering tube. And since it won't be mixed up with water, this is non-polar. Okay, so it would be collected in the test tube. Okay, so that's the setup if we want to use concentrated sulfuric acid or phosphoric acid. But here, please note that the phosphoric acid is a better catalyst than the concentrated sulfuric acid because we have learned that the concentrated sulfuric acid can be an oxidizing agent. So it might form other product than the alkene that you expected. So here, the phosphoric acid is a better choice for this reaction. Okay, so if we don't want to use a solution as a catalyst, we can also do this reaction using a solid. So here, I want you to change something on your notes. So this part, it should not be like this. It should be the aluminum oxide. Okay, so this time we can use a solid, which is the aluminum oxide, as a catalyst to do the reaction. Again, we need to heat the reactant. And then this, take a look, if we again using ethanol molecule, we will remove water here. And again, we're gonna get ethene as a product. And since here we have a solid as a catalyst, if we're still using this example, this setup, then the ethanol would not be effectively having contact with the solid, and then it would just go away, escape the system because it got a pretty low boiling point. Okay, so in order for efficient contact with a catalyst, okay, and we know it's gonna evaporate quite easily. I remember it should be below 100, the boiling point. Okay, so we use this kind of setup. So we soak the ethanol onto the bowl, and then we put it at the bottom of that test tube, and then we put the catalyst in the middle of the boiling tube, and then when we heat, we should first heat the catalyst, make sure it's warm, and then we're gonna heat this part and let the ethanol to evaporate, and when it evaporates, it will go through the catalyst and have the reaction, and then the ethane formed will then go through the delivering tube and be collected here in the test tube. Okay, so that's the second choice that you can use to do dehydration. So the reagent and the mechanism are pretty straightforward. But one thing you need to pay attention, if we have symmetric alcohol, then it's going to be easy, okay? It doesn't really matter which hydrogen it would take. But if we have asymmetric alcohol, like in this case, so which hydrogen we're going to take away? Is it the one I circle with blue or the one that I circle with green? Okay, so in order to work out which is a major product, we have to follow one of the rule called the Zayev's rule. Okay, so for the according to the Zayev's rule, the major product should be the one with greater number of alkyl groups attached to the carbon-carbon double bond. Okay, so what does that mean? So take a look at these two carbon. This one is mono-substituted. It only have one alkyl group attached to it. Okay, but look at the one on the right hand side. Okay, this one is di-substituted. You can see it got one alkyl group on the left hand side, the other one on the right hand side. So the one I highlighted with blue is more substituted, so with greater number of alkyl group attached to it. So if you see the mechanism, we need to, okay, so here first, it would attack the acid, which is a catalyst we use, and then it will have this oxonium ion. Remember, oxonium ion is very reactive, and in this case, it would just leave and then try to form a reactive carbocation. So if we have a carbocation formed, then we would like to form a carbocation with greater number of alkyl groups, so it would be able to stabilize this positive charge. Okay, so take a look at the example here. If we can form the positive charge on this carbon, okay, since it has two alkyl group attached to it, it can stabilize this carbon better than the one highlighted with red. Okay, so we will be able to remove this hydrogen, okay, to form that carbocation. So the product will be like this. So the double bond between the second carbon and the third carbon, and that's a major product. We also call it the Zayev's product. So it's more stable for this one. For NOS Zayev's product. And then if we remove the hydrogen from the carbon with less number of alkyl group, then it would be the minor product. The minor product also, you can see that it can be called as Hofmann product. Okay, and it's less stable compared to the upper one. Okay, so you need to be able to work out which one is going to be the major product. So let's take a look at some example here. So checkpoint question 1, we have 3 kinds of alcohol butane 1O, butane 2O, methyl propane 2O. Okay, so maybe I quickly show the structure so you know how it looks like. So I will not draw all the hydrogen here to save the time. So that's butane 1O, okay, and for butane 2O, will be this one. And for methyl propane 2O, okay, like this. So here, which of the following correctly arranges the three alcohols in increasing ease of dehydration? Okay, so check this example. Because we want to form stable carbocation, so it would be easier if we have tertiary alcohol. Okay, so the reactivity would be favored from tertiary, and then the least favored should be the primary alcohol. So here we just need to arrange these three from primary to tertiary. Okay, so you can quickly spot out that the first one, butane 1O, is the primary alcohol, and the second one is the secondary alcohol. Okay, this carbon attached with the hydroxyl group got two alkyl group attached to it, so that's secondary alcohol. So that should be placed in the middle. And for the one on the right hand side is tertiary alcohol. Okay, so the carbon attached to the hydroxyl group got three alkyl group attached to it, so it's tertiary alcohol. So that'd be the easiest one to do dehydration. So the correct order should be A. Okay. Okay, and then we consider the following reaction here. So we're using concentrated sulfuric acid as a catalyst, and we also heat the solution. And now we need to consider where the double bond going to be formed. Is it this carbon and the one on the left hand side, or this carbon with the one on the right hand side? Again, we're going to compare which carbon is more substituted here, the red one or the blue one. Is everyone still awake? Okay, very good. Thanks for responding my questions. So yes, correct. It should be the blue one. The blue one is more substituted. Okay, so here you can see it got 1, 2, 3 carbon attached to it, so it's tri-substituted. So the double bond should be formed between the middle carbon with the blue one. And if you check the structure, it should be C. Okay. Okay, then move on to the next one. The following alcohol is heated with excess concentrated sulfuric acid, and then it asks you to work out the Zev's product and also the Hofmann product. Okay, so X, take a look at the structure here. Okay, the carbon in the middle, which one is going to be forming the double bond with? You got two choice. Okay, these two look the same, okay, and or the other one that highlighted with blue. Okay, again, yes, this time the double bond will be formed between the middle one and the blue one. Okay, the blue one is di-substituted. Okay, the red one is monosubstituted. So the blue one is preferred. So that's going to be the ZF product here. So if we check the structure, it should be this one. Okay, so the two methyl group stays here and then form the double bond. Okay, so that's the ZF product. So for the other one, it's going to form the double bond either between this one, okay, this carbon and the methyl group here, or this methyl group. Okay, so it should be the same because we can rotate the single bond. So that matches with this product as well. Okay, so carbon with a less substituted carbon forming the double bond. So the correct answer should be C here. Okay, so this is for the dehydration part. Any question? If that looks fine, we're going to move on to the oxidation. Okay, so here, so the reaction we have just talked about is dehydration. So we're just removing water. And for question 3, okay, so we have our hydroxyl group here, and then we need to take one more hydrogen to make water. Okay, so we got 3 choices. Okay, so we can take hydrogen from here, or here, or here. It must be from the carbon that next to the one with hydroxyl group. Okay, so you got 2 type of carbon here. The one I highlighted was red. It bonded to 3 hydrogens and then the alkyl group here. But for the blue one, it bonded to 1 carbon, 2 carbons, so 2 alkyl group and 2 hydrogen atom. Okay, so for the blue one, we say it's disubstituted. But for the red one, it's monosubstituted. So the blue one has greater number of alkyl group attached to it. According to the ZF rule, the double bond should be formed between the carbon and the carbon with greater number of alkyl groups. So between this one and the blue one. Okay, so that would be the major product, which is shown here. So the minor product, the Hofmann product, would be the opposite. It would take the hydrogen from the carbon with less number of alkyl group. So it will be taken hydrogen from this one. Okay, and then it will form the double bond between this carbon and the carbon highlighted in red here. So that's the one shown on the right hand side. That's a Hofmann product. Okay, so that's the first reaction we're going to learn today. And the second one we're going to learn is called the oxidation of alcohol. So when doing oxidation, we can use a lot of oxidizing agent. But here in this syllabus, we're going to use the potassium dichromate, whatever. Okay, so we are going to use this reagent. Make sure it's acidified, and then we will get the product we want. Okay, and for this type of reaction, we need to separate it into primary alcohol, secondary alcohol, and tertiary alcohol to discuss possible products. Okay, so let's take a look at the primary alcohol here. So if we put the catalyst inside the reaction and then heat it, the primary alcohol would first turn into aldehyde. Okay, and then if we further heat it with the catalyst, we can further oxidize it to carboxylic acid. Okay, so look at an example. If we start from ethanol, after heating with catalyst, we will form ethanol. Okay, so we are going to turn the hydroxyl group into C double bond O. Okay, so remember, because we are oxidizing the hydroxyl group here, so the C double bond O will be formed at the end of the carbon chain. So we call the product in the middle the aldehyde, not the ketone. Okay, and then if we keep oxidizing this product, we will be able to form the carboxylic acid. So in this example, it would be the ethanoic acid. Like this. Okay, so 2 steps. Again, if we are going, if we have another example, the methanol here. So first, it will be oxidized to methanol. Okay, and then remember, you need to write the condition is acidified. And again, if we do it for longer time, we will be able to get the methanoic acid. Okay, so let's think about it, how we're going to do this experiment. So for no matter it's methanol or ethanol, the boiling point is not very high, and we need to heat it with the catalyst and then heat it for quite a long time to get the carboxylic acid. Okay, so but while we heat it, these 2 reactants can easily evaporate and escape the system. So to solve that problem, we need to use the setup that we have talked in the previous lesson, the reflux setup here. Okay, so for example, the methanol here, the boiling point is around 65 degree. Okay, so pretty low boiling point. It's gonna evaporate quite readily. But if we're using a reflux setup, once it evaporates, it will touch the cold condenser. Okay, and then it will condense back to liquid and then drop down to the round bottom flask for the reaction to continue. Okay, so in this case, we can make sure all the alcohol has been turned into aldehyde and then further turned into carboxylic acid. Okay, so this setup heating under reflux is to obtain carboxylic acid, the final product here. Okay, so we make sure all the reactants stay in the round bottom flask and we push it to complete. Okay, so therefore alcohol should be heated under reflux. Okay, this one, the catalyst. This is a catalyst we use, okay, to make sure that it turns into aldehyde and then further into carboxylic acid. Okay, but sometimes we don't want to get carboxylic acid. We just want to oxidize it to aldehyde. So how can we get aldehyde out here? Okay, we want the aldehyde, once it formed, it will leave the system so that we can collect it. Okay, so how do we do that? If we take a look at the structure here, for alcohol, it will be able to form hydrogen bond with another alcohol molecule because it got oxygen, which have lone pairs on it. It also have hydrogen that attach to the oxygen. So for example, here we have methanol. This methanol can form a hydrogen bond to another methanol. Okay, but if we take a look at the methanol here, it only have oxygen that has lone pair to it, but it doesn't have any hydrogen bonded to the oxygen. So for aldehyde formed in the middle, it will not be able to form hydrogen bond to its molecule. So the aldehyde formed should have lower boiling point compared to the alcohol. Okay, so by considering the difference in their boiling point, we will be able to separate the aldehyde from the alcohol. Okay, so here we're going to use a different setup. So this setup is called distillation. So the setup, if we compare with a heating under reflux, the only difference is that we put the condenser at a different position. Here we put the condenser vertically. Okay, so when the organic reactant evaporate, it's gonna condense back to the round bottom flask. But here, if the organic solvent, for example, aldehyde, evaporate, it will go this way. And once it touches the condenser, it will not be able to go back to the round bottom flask. It will follow this tube and then be collected in this conical flask. Okay, so that's a major difference between these two. And remember, we have a difference between the boiling point of the methanol and the methanol. Okay, what methanol can form hydrogen bond, hence it has higher boiling point. Methanol doesn't have cannot form hydrogen bond, hence it has lower boiling point. So if we can set the temperature at a right number, then we can get the methanol to condense back here, but not the methanol. Okay, the alcohol will not evaporate. We need to control the temperature precisely to make sure alcohol will not evaporate, but the aldehyde will evaporate and go through the condenser and be collected here. Okay, so that's a different setup used for this part, oxidation of alcohol. So for this one, this setup, we call it distillation. Okay, so the slash here means it's acidified. Okay, so we're not just going to put the catalyst, but make sure it needs to be acidified. Okay, so we got time. I will quickly show you the video. Pay attention to the color change of the catalyst. All right, so that's for would you be able to hear what he is talking? Okay, doesn't matter. I'm going to explain it. So that's a setup for reflux. Oops. Okay, so you can see the condenser is put vertically, and you can see clear. You can see a clear color change in the round bottom flask. That shows oxidation has taken place. Okay, and then when the aldehyde evaporate, remember aldehyde got a lower boiling point, then it will go up and touch the condenser, and then it will drop down to the round bottom flask. So the reaction will continue. If you leave it for some time, it will go eventually to carboxylic acid. That's for the heating under reflux. Okay, so make sure if you do reflux, the water should go in from the bottom and leave the condenser from the top. This is to make sure that the condenser is filled in with cold tap running water. Okay? And then if we move to the distillation, so that's a setup for distillation. Now we put the condenser horizontally, and we tilt it for a little bit so that we can collect the aldehyde in the round bottom flask on the right hand side. Again, for the distillation, we still need to let the water go in from the bottom, so it will fill in the condenser. Okay, fill in the condenser with the cold running tap water, and we should leave on top. Okay, and we need to carefully look at what he is doing now. Okay, he's not going to leave the Bunsen burner just under the round bottom flask. Okay, because we need to carefully monitor the temperature. The temperature should be between the boiling point of the alcohol and the aldehyde to make sure only aldehyde would evaporate and go through the condenser. Okay, and clearly you can see that color change that shows oxidation has taken place. And then if you wait for some time, pay attention to the round bottom flask on the right hand side, you will see aldehyde drop in. Let's see. Yes, okay, pay attention. On the right hand side, we're going to get the aldehyde. Okay, so if we're zooming a little bit, you can see the aldehyde is being collected in that round bottom flask. Yeah. Most of the organosolvent is colorless. So if you're dealing with organic reactions in the lab, it's quite hard to monitor the color or monitor the reaction by color change unless you're putting some inorganic reactants to it. For example, this time we have the catalyst that shows a clear color change. Okay, so this is a two different setup for doing oxidation for alcohol. Okay, so here we have discussed what's going to happen if we have primary alcohol. Okay, if we have secondary alcohol, then it will only oxidize it to ketone. So if we have propanol here, propanol, then after oxidation, we are going to get this one. Let me finish showing the structure. Okay, so after the reaction, we're going to get propanol. Okay, and we are going to stop at ketone. Because if we have carboxylic acid, that need to be at the end of the carbon chain. But here we have the C double bond O in the middle of the carbon chain. So we would not be able to further oxidize it to carboxylic acid. Okay, and then you can try this one. What is the product? Make sure you write the condition. And we only got less than a minute, so I will start a new meeting and let you to join in. I want to finish this part for today before we leave. Okay, so while waiting, please try that one, that question.